Hi everyone, thank you so much for being here. I understand there's a lot of things to do in any afternoon, so I appreciate you all taking the time. Thanks so much, Dhaval, for the introduction and to your team for organizing this event wonderfully. Just by show of hands, how many of you are building GenAI applications? Oh, I thought it would be like the whole room. How about classical machine learning? How many of you have to choose databases for, either machine learning or just in general? Like you have a number of choices and you gotta choose. And then how many of you have to build databases? Cool. So there are very few people who decide to build databases, and we'll go through the reasons why. But what I want to talk today about is how we started down the path of building a specialized database that would be for machine learning applications. We got started back at Intel a few years ago when we were looking at, we were part of this science and technology center that was addressing how do you change cloud systems when the primary data types are going to be unstructured data types. So in that case, it was images and videos. And the workloads were going to be machine learning kind of workloads. You're querying data frequently, you're creating data sets, you're training models, you are using the trained models to enhance the data. So that was a change in pattern, change in industry landscape and change in pattern that put us down this path of defining, how can we solve problems for data scientists and machine learning engineers and data engineers. So let's start from fundamentals that, I guess for most of you, they're probably just repeated. So I like to start from in my mind, what does it mean to be working on multimodal AI? Essentially, boiling down to the simple terms, because I don't actually develop models, it's when you take various different data types to come up with an outcome that you care about. You're trying to mimic human brain in this case, and we look at things, we hear things, we read things, and that's how we arrive at whatever decisions and things that we do. That naturally leads you to multimodal data. And the classic example that I always think about is doctor's office. Doctors always, very frequently to diagnose something, they'll require CT scans. They'll take your pulse. They'll be like, go like show your tongue and see what's going on. So they'll collect different types of data, and those are essentially different modalities of data that you deal with. And you need a combination to arrive at results that are more real or more like how we would decide certain things. Now, as we we just had a question on vector databases. Lately, there's no escaping embeddings, and the reason why is because naturally the different modalities of data are not the easiest to search for. It's hard to say I want to find images where the pixel areas match. You can do it as humans when you're looking at it, but you can't do it at scale. So another solution to that is you find a way to change all these data types into signatures that are lower dimensional representations, and then you use databases for matching so that you can land in the vicinity of the data that you're looking for and then sift through and reorder for exactly what you're looking for. So that's why I say that embeddings have become like a new and more scalable way to sift through really large data types and data collections. Now, naturally, that leads us to vector databases because their primary function is to allow you to index these high-dimensional representations and support near-neighbor searches. So they'll take those signatures and go find what's the closest cluster to what I'm looking for. And once you find the nearest cluster, if you've labeled them, you can also classify, okay, whatever you're showing me must be a picture of this. So that makes vector databases really powerful in terms of what they do. But then, and that explains, and this is not even like half of them at this point. I think as of last count, there were probably like 40 or 50 odd vector databases out there in the market. So what's missing? Why do we keep seeing new ones all the time? Let's take some examples. And this example has become very common across industries. You have, there is a certain error code. A customer goes on a chatbot that somebody created with like the latest LLM with the vectors indexed in some vector database. And now they're asking, I want to understand what this error code means. And not only do I want to understand that, I only want information about equipment manufactured between 22 and 23. And I want the authors to be from a specific team. And not only that, I also want to see the documents and the data that matched all of this. So very quickly, from the very first step where you were just going to do a simple vector search, you went down to filtering on metadata, like you're putting timing constraint, you're putting author constraint, and now you're saying you want the data as well. That's just one example. Let's take a classical machine learning example because that's not gone away. That's just starting to see its light in production here. This comes from one of our customers where they want to find products that are similar, but they want to restrict it to the fall 2023 catalog, and they also want to show you the pictures of that product, and maybe there are videos recorded of that particular product. So not only do you find by similarity, because you can take the picture of whatever you're looking for, find similar things, then you have to restrict by metadata, and then you actually have to find similar looking other images. And before they can get to support all of this stuff, they have to create and manage the data set. So they have to catalog. They might have millions of products, millions of images corresponding to those products. They have to catalog those. They need to be able to search. They need to be able to train their models, which will then extract the embeddings that you can use to search for all of these things. The reason I'm telling you all this is you can go through different verticals, different use cases, as we've been doing for some time. And what you realize is indexing and searching over high-dimensional vector space is very important, but equally important is the fact that you are going to have some contextual metadata that you have to filter on, and you will require the data itself. And you can't just do it once. You're going to be iterating over it, needing it to improve any solutions and systems you've built. So essentially the expectations from the data layers that you're going to be deploying come down to high throughput vector search and classification. And in fact, I should say it's not just high throughput, it's also low latency in some cases. You want to be able to filter on rich and evolving metadata. Because remember, the better your models get, the more information you can automatically extract from your existing data and make it better. And then, of course, you want to be able to connect with the original data. You want to do all of this stuff reliably and at scale if you want to have any hopes of deploying it in production. And then there's the usual enterprise-ready, cloud-agnostic, sometimes deployed in the VPC. And these are requirements, ideally, for one data layer and not 5 of them connected together. And so if I go back to why is something missing despite all these vector databases, the vector databases let you index. It's not easy to have high-dimensional indexing and search be done at scale. But they do that very well, but they're missing support for complex schemas. There isn't very good support for multimodal data itself. They are very much focused on the query at the end. You are going to do a LangChain or Llama index sort of framework on top. You're going to do some vector search query. It's more focused on the query side, not necessarily how is all of this stuff going to evolve across the machine learning pipeline. And then, of course, every time you go to choose a tool, you got to make decisions based on whether it's on, can it be done in my VPC? Is it scalable? Does it have all the enterprise support I need? And if you trace back, like if we were to just chart the path of how people build their data systems, step by step, let's start from input data, and let's start from the fact that you're going to go to certain output that you need. Invariably, the steps that you'll encounter, you take the metadata, put it in some sort of, you take the data, put it in some form of storage. Very frequently, it's S3 buckets, Google Cloud bucket, and the metadata lands in a choice of relational, graph, key-value database. Then, sometimes you need labeling or annotations. People are literally passing around buckets of data to the labelers, even if they are in-house or external, and then they take annotations. And some people land them in other databases. Some people just scan through buckets every time to look for what they are, to search by labels. And after that is when data scientists are writing their own scripts to query data from these different systems. Data engineers are writing their own scripts to query data. Sometimes when you're dealing with image, video, audio data, you're kind of processing it to bring it in the format you want. And that's where the vector database piece fits, because that's when you get to the query part of it. You've extracted the embeddings and you go put them. So even though you are trying to choose the best tool for the specific data type, look at the DIY spaghetti that we are in at this point. And unfortunately, this is status quo and very hard to displace because, well, you put in all the effort to do this, but you're paying a constant price. And the prices become higher because AI model development is moving so fast. If you take 6 to 9 months to set that up, I think you probably have missed like 3 versions of OpenAI models, 2 or 3 versions of Anthropic models, and you're like really falling behind, right? That's essentially this spaghetti diagram, combined with the fact that it was not software engineers who were expected to deal with this, it was data scientists and data engineers who had to, along with the fact that they had to train the models and use the data for driving some downstream business application, that motivated us to see what can be done for it. And given that our background is in system software, we took a system software or a database approach and looked at the entire machine learning pipeline from data ingestion to queries to come up with certain elements that would belong in a data management system. So the very first thing we realized is, granted there are, we should offer native support for multimodal data types. Now we started with images and videos, which is why we even have processing functions or processing operators in our query language to allow you to do things like, if I'm fetching a video, give me specific frames that I care about. Or for an image, transform it into this thumbnail size before you return it to me, just so you could do the data processing close to where the data lives. So that's why, that's why we didn't want to leave it in any generic cloud store or file systems, because you could offer things like that. And let me show you what happens if we did leave them in wherever the different buckets that they were stored in, right? Now that looks complicated, but that's nothing in terms of what really happens. So working with some large enterprises, you get exposed to certain challenges which you never thought were possible, right? Let's say the data scientists want to create specific data set. It could be for fine-tuning, training, inference. It could be for some GenAI application. Look at the things they need to go through. First, they have to figure, where is the reference information? Which database tables refer to, if I go back to that image example with the retailer, which database tables have the product information that will have the URL to where the images live. After that, I need to get permissions to access those buckets wherever the data actually lives. Then I need to be able to download it, because I'm not getting this permission for a long time. So downloading all that image, you gotta have allocate a machine big enough for these resources, and then you start creating different data sets. So maybe I was creating a data set for area rug and for SOPA sets, and there might be some overlap there. So I create data sets with overlaps, and every time I need to reformat the data, I'm creating a copy. So not only have you lost time in getting all these permissions, increased cost because of the numerous copies of data, you've actually, the worst thing in such cases, hurt the compliance requirements, because you don't even know how many places the data is replicated. If someone asks you to delete it, good luck. And so in fact, what we realized, and this was startling to us, is people didn't want to change. Once they had the data set with them, no matter how much new data was added, they didn't want to go back and update it. So of course, and then they were supposed to train models. They didn't have access to all the data, and they weren't ready to go and get more data because of the amount of time, because they only had 3 months to develop the model. The outcome was subpar. And who got blamed? Well, the AI models don't work. So that's the reality. And this is you can think about it just with text. It gets even more painful when it's images and videos. Because every time you want to do something with videos, you're thinking about, oh, one video is 2 gigabytes. And all I need are 30-second clips out of it, but I'm going to have to download the whole thing. So that was the data piece of it. Then we realized all of the data comes with really relevant metadata. Even if you fundamentally just ingested images or text files, they'll have at the minimum timestamps. They'll have maybe some author information, some source information. And that can really help you start to narrow down on subsets of the data you need. And we wanted something, so that's why we went down this path of how do you store metadata. And our choice was a graph database. Why did we choose a property graph database and why did we build our own? So I want to show you a few examples of, we ran through a lot of different applications. We started all the way from like a medical imaging application, a retail application, sports and media application. And every time we ran into connected data. So if I walk you through just some examples here, this is a transportation example. You have a carrier that organizes freights, maybe there's an insurance claim, there are some images for it, and there might be some PDF summary files. So this is naturally connected. If you were to represent it in today's databases, you would be creating multiple tables and putting foreign keys across them. Then we looked at another aspect of it. If you're talking of machine learning applications, the better your models get, the more information you can naturally and automate extraction of, which means this can constantly evolve. So you can introduce new entities, you can create data sets, you can indicate what models were trained on your data set. Heck, you can go and introduce new properties or change these values. It's something you want to do, but it becomes really hard with a very tied down relational schema. So some of these aspects made us realize that graph data model was really good. But traditionally, graph databases have problems with operating on disks because they can make them really slow because it's all, you're traversing relationships which can be really slow on disks. But we had the opportunity back at Intel to build an in-memory graph database from scratch. And so that's what helped, so we were down the path, we were able to build a property graph database from scratch. And that led us to a database that was not only low latency in queries, you could actually do really fast lookups in large data sets. We could scale to billions of objects, and we could achieve really high throughput for a graph database compared to, at the time we were comparing it to Neo4j, the community edition. And there were queries that we would be 80 times faster, simply because we were built for in-memory operations. And so because we could use that, we did the graph database as part of the metadata search, and we stored all the metadata in the graph database for advanced searches. But then we realized there is another aspect of search that when you're dealing with multimodal data, you can support, and that's searching by similarities. Because you could convert images or videos or audio or even text into those signatures and enable high-dimensional searches, find approximately what you're looking for, and then maybe do better filtering with the graph that you have. So that's how we introduced VectorDB within ApertureDB. We built it on top of Meta's face library, but introduced durability, transactional support on top of it, and we were able to use all the API that face offered. So that's why we can support approximate and exact searches. We can do different engines and different distance metrics, and we were able to build it to be faster than some of the most popular vector databases out there. So that was the third essential component of building this data system. Now there was another key piece that we realized, if we don't do this, then we are really plunging people back into the DIY solution, and that was unifying all of them behind one query engine. And this actually turned out to be a very complex piece because we wanted to support asset transaction or the whole atomicity, consistency, and all the durability guarantees across so many different data types and in these sort of systems. So this piece was very interesting to build, but what this allowed us to do is no matter the data type that people are dealing with, they are able to store it in ApertureDB and they can index enough information to search and find what they're needing, and then over time we'll be able to support operations to get it to them in the format they need, which is what has allowed us to offer unified multimodal data backend. We allow multimodal searches here, and we've been able to build over time capabilities to manage data sets, correlate models with data sets. In fact, one piece that keeps coming up nowadays is data governance. And if you imagine because you start out with everything represented in the graph, you can actually maintain how data got transformed to, what was the lineage of it, and you can go back and track in the graph what happened, and you can enable all the access control and privacy guarantees because you can restrict access. The searches are going through the graph for everything in the database. So building a system like that basically has allowed us to help people do their AI development with all of their data. You don't have to compromise on, I can only use this subset of data or a specific, or I can only work on a specific part of the pipeline. The idea is you put in all the data types and you're able to feed it into your entire machine learning workflow and improve it much faster. And did we really achieve some of the, did these design choices make a difference? Yes. Sometime back we did a study comparing ApertureDB and all the things it can do with a DIY solution. We used Postgres, we tried it with MySQL because some of the numbers were shocking even to us. Like, did we fine tune it properly? And we were able to be 35 times faster into creating data sets because a lot of the time you query, you access data, you prepare data, or you're processing the data. And all that is cost that you have to pay, which you can really optimize when you build a database focused, specialized for a task. In fact, we got some really good surprises in terms of data transfer reduction. So because most of the time you're scaling data down to the formats you need, you do it near the data, which means on the network, you're transferring less data. So especially in image video kind of use cases, we get 63% all the way to 6x reduction depending on how high resolution your original data is and what you're intending to do. There are other benefits. Of course, the big thing is you can actually now set up your data infrastructure much faster. And we have been able to scale the database, and this is not even the upper limit. This is just how far we've tested. 2 billion objects, over 300 million images, over millions of 4K dimension embeddings. And the test is they are still ongoing. It depends on how big our customer workloads get. Just to kind of wrap up the example that I used early on for the retailer, the reason they started working with us was the productivity. So I never make a claim that you cannot do this with the existing tools. It's just, do you want to spend the time, and do you want to waste your time doing all this stuff that can be wrapped up in a neat package? So some of the common tasks that they used to do, they used to take days or hours sometimes. They didn't have a good way to share embedding because this was a few years ago. And now it's become basically, they just write queries against the database, which is really convenient because most of the time is now spent in machine learning. So in general, did we simplify the life of data scientists and engineers with our design choices? Let's just go through and see. We did build a simple dashboard to allow you to see your graph metadata, so you can see what objects there are, what types they are they indexed or not, what are the properties, what's the number. This is a very useful dashboard because one thing we realized a few years ago is data engineers and data scientists are in different teams very frequently in large companies at least, and they get confused on what the data types are or what the property names are, and therefore different teams end up introducing the same thing in different data types. So like one is ID is integer and one ID is string, and that shockingly can lead to a lot of wasted time because the data scientists are querying with one type. They're telling the data engineers we're not finding the data, and nobody knows how to debug this. And then eventually some third party realizes, oh, you have two product IDs. So this is a dashboard that helps you to see all of the things that are there in the database. Then another thing we learned, and these are just like surprising learnings as a systems person sometimes. It's like, oh, we can't develop our models really well because we can't see all the images. We tried to build a dashboard, we could do a few queries. So we looked at like 10 images out of the million, and we just approximated how we had to tune the model. And our project got canceled 3 months later. And I'm like, okay. So that's we started off with we have image search. You should be able to, you can navigate your images. We have a similar tab for video search. And this is just we are building it just to help people navigate their complex data sets more easily. You can, of course, ask questions. So you can build RAG pipelines on the vector search. You can, in fact, use the graph to optimize your responses now with graph RAG techniques. You can search with multimodal embeddings. Our vector database supports text and multimodal embeddings. So you can ask questions like, oh, I want pictures of pizza with friends, and then create data sets with that. We can whittle down complex data set preparation to minutes. And this was motivated from early research in terms of a data scientist saying, all I need are the key frames from my video. But every time I have to download the whole video, run through the decoding and extract that. And we're like, we have to do something about it. So while that query language looks complicated, ultimately you can see that you can just extract the interesting frames that you need for the sort of processing. And this becomes easier once we explain it. We've just been working on how well to explain this. And then, you work with PyTorch, TensorFlow, Vertex AI, any of these things. Data set is just this concept. You write the filter. That's all the user needs to do. And then it's the ApertureDB data set that will go split and pipeline into batches and feed it into the models as they are running. You can debug your data sets easily. You can see what annotations are there, what segmentation masks are there, and various different things. So hopefully that can help you understand what labels you might be missing. Or we could plug it into something like a box of 51 to help you see the distribution. And ultimately we realized databases live in an ecosystem. So we have been adding integrations to make sure that people can integrate with different labeling tools. They can feed it into different visualization and query frameworks so that it's really easy to get started with their machine learning deployments, regardless of how complicated their data might be. So bottom line, if you remove that data complexity, you can take all those days and hours from data set preparation and dedicate that into fine-tuning the machine learning and AI side of it. Why did we still need to build all this stuff? Because as much as there are all these tools, we realized they were missing the perspective of the entire pipeline. If you take the view of the entire pipeline, then that is essentially where ApertureDB is where you land, because that's what people try to create with their DIY solution. So that's how we built our database for multimodal AI. If anyone has their laptops open, I would love to have you try ApertureData.io/demo request, try it out, or try our chatbot on the documentation. We are looking for feedback all the time. Any questions?
We're going to give the mic.
Thank you so much. It's pretty cool what you built. Appreciate that sharing. I had a question on the metadata part that you talked more related to the privacy and attribution of user who uses it. Are you tagging the data that goes, the copies, and everywhere it's being used right now to be able to comply with privacy regulations, or is that something coming up in future?
It's more coming up in the future. Right now we can log who accessed what, but because you can introduce those things in the graph, it is something that we put in our roadmap, like depending on enterprise deployment levels, we'll be able to enable that.
Okay. Are you looking to integrate with existing solutions that allow the tagging, or are you trying to build it in-house?
No, we are open to it. We try to reuse what we can. Like some of the fundamental layers that we built on Metaspace, like we did write vector search from scratch. So we try to use some of the core components if we can. So yeah, there is something that we can use. It's something that's down in our roadmap after our upcoming launch in October.
Okay, thank you.
So just to make sure I understood that correctly. So right now, it's basically single instance. You don't have the ability to segment your data from customer to customer. You're putting customer data in here.
Oh no. Okay. So the database is distributed. There are different components. So we have scaled it out at this point. And for different customer deployments, we right now are segregating it in different, we create different instances.
Okay.
So we don't put we don't put multiple customers' data in the same database instance.
And you're saying that is on the roadmap to have single instance, multi-customer?
That, yes. I mean, we are launching a cloud product soon, so a self-service cloud product, and that's going to be like a part of the
Here.
ApertureData.io/demo-request. There are three options depending on whether you want to see celebrity faces, you want to see Coco dog cat images, or try out our land chain. You can choose one of the three.
I had a question. Thank you. Great presentation. A lot of good insights. What was not very clear to me is this is obviously an evolution of a graph database, right? What you've built.
It started like so. Graph database is one of the components.
Okay.
We actually debated should we use the graph database we built or should we go with the relational for the metadata. Our problem was to find a place to land the metadata. We ended up going with the graph store because the data model made sense and we were able to make it fast. If it hadn't been fast and it couldn't support the volume, then we would have gone with the relational.
Okay. So next question was, since it's an in-memory database and you are much faster, what is the cost of running this compared to other systems? Like, do you need systems with large memory to be able to?
Depending on the graph sizes, like for example, I think the numbers would have changed right now, but we had once, I think the billion scale that I mentioned. I think there was the footprint was in like some. We needed a 128 gig machine or 256 gig machine to support that because of the in-memory nature of it. Now we can of course we do persist the data. So if you're not fetching the entire graph, you could start out with smaller memory. But yeah, the memory is where we pay the price. But given this type of applications, it's a fair thing to do. We're not trying to run this on the edge yet. We can run on the edge if you're not going to use that much metadata, but most of the time these are server applications.
Just curious, like during the ingestion phase, is the embedding creation of all the modalities interdependent on one another, or are they still segregated? Like, I was just wondering whether you use the hints from one modality to like improve the ingestion for the others, or like something like that.
Right now we do so a lot of the metadata and the embeddings, they right now come from our users. Primarily because they're so domain specific. In the same picture, someone cares about the person, someone cares about the furniture.
Yep.
So we let users define. What we have done is build some simple like ETL tooling around it, where you can specify what model you want to use on which data type. But it's done like when you are, let's say, ingesting images. You could run clip embedding, and you could run some other maybe it's a FaceNet data set, maybe some FaceNet model embeddings in the same pipeline, and it'll add the image along with the two different embeddings at the same time. But we're not we're not saying, put anything learned from one sort of model run to another model.
Also, like related to this as well, like during RAG pipelines, in the retrieval phase, do you sort of is the user sort of conditioning the database to like only output data like from one modality, or if it is like multiple modalities, how do you sort of rank the different modalities together?
So that logic right now is more on the client side. So for example, the example we built there with LangChain, it queries for the documents and then it does MMR ranking outside. Okay. Our idea is as we start seeing more patterns emerge and we need to optimize something, we'll pull it into the database side. But right now, you query different modalities. One of the things that we've been considering is like, can we offer an API that lets you weight, like attach different weights? So like, just a pure embedding search for image versus a multimodal embedding search. Can you attach different weights and then order the result on server side? That's something that we just need a driving application.
Okay, thank you.
Do you have kind of benchmarking with the other graph DB? And what I do understand, like we can just use unstructured data and then your system will just like help us like clean all of those, or we have to clean it first.
So benchmarking against graph databases?
Yeah, the other
graph. Neo4j sometime back, not recently.
Yes. Oh, okay.
But that sometime back was before our production ready product.
Yes.
And there were certain queries that would be like 80 times faster in latency.
Oh.
And throughput would be like at least 2x, 4x, 8x, depending on the workload. All these things, unfortunately, I have to keep saying it depends on your application, which seems like a cop-out, but that's the reality of it, especially with these data types. And then in terms of, can you just point us to a collection of, unstructured data, and will we extract the information? Not at the moment. We are
Okay.
exploring integrations with certain tools to help us do that, but right now we do rely on, we make it easy for you to specify, this is my logic to extract it, but we don't offer that logic yet.
I see. Okay. Thanks.
I think the database took long enough. And now we want to just partner with people.
Thank you, Vishakha.
Thank you so much.